This call is now being recorded. Okay, good afternoon, everyone. We are still on chapter 7, and that is actually point estimation. So, this chapter, we're going to deal. We have two parts here. First, we're going to learn about the methods of finding an estimator. And then, secondly, we're going to uh, evaluate these estimators. So, we have here our definition. A point estimator is any function of our sample or function of our random variables x sub 1 up to x sub n. So a statistic is a point estimator. And then if we're going to consider the realized value uh, no, of our point estimator or realized value of our random variables here, we have small letters x sub 1 up to x sub n. The point estimator is actually an estimator of our unknown population parameter theta, or sometimes it could also be uh, an estimator of a function of our unknown parameter theta. So the first method for finding estimators, we have the method of moments here. We're going to equate the first k sample moments to the corresponding k population moments. And we have here the corresponding formula for the sample moments, the kth up to the kth sample moments, as well as the formula in determining the kth population moments. So the k sample moments is being denoted by small m sub k, while the kth population moment rather is denoted by mu sub k prime. And then the then we're going to equate these k sample moments with the k population moments. So we have there in 7.2.2. We have an example illustrating this method. Suppose we have a random sample coming from a normal distribution with mean theta and variance sigma square. Uh, okay, so both are unknown, the mean and the variance. So we're going to use, no, we're going to find the uh, first and the second sample moments, as well as the first and the second population moments. So here on the right hand side, we have here the first sample moment, m sub 1, which is actually equal to the sample mean. The second sample moment, m sub 2, we have 1 over n, the summation of x sub I square. And at the same time, for the first population moment, mu sub 1 prime, by definition, we have the expectation of x, and that is equal to theta. Okay, the mean, theta. And then mu sub 2 prime, the expectation of x squared, and using the definition of a variance, so the expectation of x squared will just be equal to the variance of x plus the square of the expectation of x. And then solving for that, or equating, no, the first sample moments with the first population moment, as well as the second sample moment and the second population moment, we're able to determine the method of moments estimators. Okay, so the notation for the method of moments, instead of hot, we have here the tilde over our parameter. So in this case, we have theta tilde. Okay, this is the method of moment estimator of our parameter theta. And then sigma squared tilde. So this is the method of moments estimator of our unknown parameter sigma square. So we use the tilde, no, if we are using the method of moment uh, technique. Let's proceed to the next example. Say we have a binomial method of moments. Let x sub 1 up to x sub n be IID coming from a binomial distribution with k number of trials and the probability of success p. So that is, we have here the probability mass function of a binomial random variable x sub I. So we have here a combination of k taking x, the probability of p raised to x, 1 minus p raised to k minus x, were the possible values of x from 0, 1 up to k, or in other words, this is the support of our random variable x sub I. Okay, so here we assume that both k and p are unknown, and we desire the point estimators for both parameter. Okay, so if we're going to solve for the first sample moment, we have m sub 1, by definition 1 over n, the summation of x sub I from 1 up to n. Okay, so in this case, it is equal to the sample mean x bar. Same, no? In our previous example, for the second sample moment, 1 over n, the summation of x sub I square I from 1 up to n. While for the first population moment, mu sub 1 prime, we have the expectation of x. Okay, the expectation of x, and in this case, it is equal to kp. Okay, the number of trials times the probability of success p. And then the second population moment, mu sub 2 prime, we have the expectation of x square, and this is equal to the variance of x plus the square of the expectation of x. Okay, so in this case, the variance of x, we have k, the number of trials, k times the probability of success, p, times the probability of failure, 1 minus p, and then plus 1 minus p quantity square. Okay, so these are the sample moments as well as the population moments. Then we're going to equate. So we have x bar is equal to kp, and then the second sample moment equal to the second population moment. So we have a system of equations here in two unknowns, k and p. So we now uh, going to solve for k as well as p. K as well as p. So after a little algebra, it says here, little algebra, we obtain the method of moments estimators, which is equal to k tilde, and it is equal to this expression, and the p tilde is equal to x bar over k tilde. Okay, so yan yung ating solution, because it says here after a little algebra. In other words, if we're going to express this expression here, we could have 1 over n, the summation of xi quantity square. Then we have kp, 1 minus kp over k, and then plus kp quantity square. So we can express this as the sample mean, x bar, 1 minus x bar over k, then plus x bar square. And then using this expression, we can now obtain our k tilde. It says there after a little algebra. It's just a little manipulation, no? Of these algebraic expressions. Pwede naman may express yan from this, no? From this, we could arrive at this expression, x square, di ba? Pwede naman natin yan i-distribute yan. So we have here x bar, and then plus x bar square over k plus x. So we have here over k, then we have x bar, and then minus 1 over n, the summation of xi quantity square, and then plus the square of x bar. Okay, so a little manipulation from that, and then we could obtain now the value of k tilde. Okay, k tilde. And then after that, we can now compute for the maximum, or not rather, but the method of moments estimator P tilde to be equal to X bar over K tilde. Ano gusto niyo ipapakita pa natin to form ang solution na to? Apart. Say we have here X bar, no? Minus, in this case, we could have 1 over n, the summation of xi square, plus, factor na lang natin muna. Mamaya na lang. Say 1 over n, 1 over n, then we have minus 1 over n, the summation of xi, and then we have here X bar. Okay? Plus pala yan, plus. And then after that, we could have a sample mean. Then we have here say minus. We have 1 over n, the summation of xi square, and minus 1 over n, the summation of xi, then x bar, and then say we can continue this, x bar minus 1 over n, the summation of xi square, minus 2, okay? Say 2x bar, then we have here 1 over n, the summation of xi, and then plus. So ang remaining niya, we have here xn, then we have x bar, then we have 1 over n, the summation of xi. And then, a little manipulation pa yan, no? Until we arrive at the value of k tilde equal to this expression here. And then using the first equation above, then we can have p tilde to be equal to x bar over k tilde. Madali lang ito. Itong part na to dito, no? Itong part na itong 3 dots, that. So you try to manipulate that until you're going to arrive at the value of k tilde and then p tilde. So these are the method of moments estimators of our of our random sample coming from a binomial distribution with k number of trials and the probability of success p. Both k and p are unknowns. Okay, so any questions or clarifications for the first technique of finding our point estimator of the unknown parameter or parameters? None so far?
Yes, sir.
Okay, so let us proceed to the next method. We have the maximum likelihood estimator. It is actually the most popular technique for deriving estimators. So recall that if we have x sub 1 up to x sub n, these are IID sample from a population with a PDF or TMF, small f of x given the parameters theta sub 1 up to theta sub k. So the likelihood function is defined by, this is our function now, the likelihood function of theta given x. It's actually a function of theta. So in this case, our theta here is actually a vector of parameters. So bold yata yan siya. So it's a vector of parameters theta 1 up to theta k. So we can express it in this likelihood function. Okay, ito. And it is equal to the product of the probability density function or probability mass function I from 1 up to n. So if we're going to determine the maximum likelihood estimators of our parameters theta sub 1 up to theta sub k, okay? So if the likelihood function is differentiable in theta sub I, then the possible candidates for the maximum likelihood estimate are the values, no? The maximum likelihood estimate are the values of theta 1 up to theta sub k that solve this equation 7.2.4. So we have here the partial derivative of our likelihood function of theta given x with respect to theta sub I equal to 0, I from 1 up to k. So in other words, we have k sin, no, k no, we have k number of equations in our systems of equations. Note that the solution, no, the solution to our equations or system of equations 7.2.4 are only possible candidates for the maximum likelihood estimate, since the first derivative being 0 is the only necessary condition for the maximum. So furthermore, the zeros of the first derivative locate only the extreme points in the interior of the domain of the function. Only the extreme points, that would mean we could only find the local, no, the local minimum or the local extremum, and then we're on the boundary, no, on the boundary of our likelihood function. So points at which the first derivative are 0 may be a local or a global minima, local or global maxima, or inflection points. But our goal here is to be able to find the global maximum. If you can still remember in calculus, if you have given a function, then if you're going to take the derivative of this function with respect to a variable, say variable x, and then if we're going to equate that to 0, then we could determine the possible critical points of our function. So these critical points could either be a local maximum, a local minimum, no, or it could be a inflection point. But if we're going to evaluate it on the boundary of our interval, then we could able or we could find the global maxima as well as the global minima. Say, let's have an example here. The normal likelihood, let x sub 1 up to x sub n be IID, normally distributed with mean theta, variance is equal to 1. And then we have the likelihood function here, L of theta. So in this case, theta here refers only to the parameter theta, which is the mean, no, the mean of our distribution. Hindi ito siya bold, no, hindi ito bold. So it refers only to the parameter theta, which is the mean of our distribution. So if we're going to determine the likelihood function, so we have here the joint PDF. So the product of this PDF. So we get this. I'm sorry. So we get this expression now. Okay, that is our likelihood function. Then after that, we're going to take the derivative of our likelihood function with respect to theta and equate that to 0. And this would reduce to this finite summation of x sub I minus theta, I from 1 up to n, to be equal to 0. Okay? So say, for example, if we're going to evaluate now the derivative of our likelihood function of theta given x, so we have here bold, from here, no, from here, so this is equal to 1 over 2 pi raised to n over 2, and then with respect to theta tayo, so we have an exponential function with the parameter theta, so we have to copy it, e or exponential, negative 1/2. So negative 1/2. We have here the summation I from 1 up to n. We have here xi minus theta. So we have here times 2. So meron tayong times 2 dyan. Times 2. And then we have 1. And then take the derivative of negative theta. So we have negative 1 times negative 1. Sorry. Mali pa pala. We have that 2. Copy, yeah. Sorry. You need to copy first. Negative 1/2. We have here the summation I from 1 up to n. And then the derivative of this using the chain rule. So we have negative 1/2 times 2. The derivative of the summation is equal to the summation of the derivative. That is why we have here x sub I minus theta quantity raised to 1, and then times the derivative of negative theta, we have negative 1. Okay, then equate this to 0. Or in other words, we have this one will cancel out. We have here positive. So we have now the summation of x sub I minus theta I from 1 up to n divided by 2 pi raised to n over 2. Then we have here the exponential of positive 1/2, the summation of xi minus theta square I from 1 up to n. Then equate this to 0. Obviously, we have this results. So we have now the summation of x sub I minus theta I from 1 up to n equal to 0. So this would further imply that we have here the summation, okay, summation of x sub I from 1 up to n minus n theta is equal to 0. So theta will be equal to 1 over n, the summation of x sub I from 1 up to n, and this is equal to uh, x bar. So this is just a candidate. Okay, it's a candidate for a local extremum. So we have a solution now that our theta hat is equal to the sample mean x bar. X bar is a candidate for the maximum likelihood estimate of our population parameter theta. So to verify that the sample mean is in fact a global maximum of the likelihood function, so we can use the following argument. First, note that our theta hat is equal to the sample mean is the only solution to our equation, no, to this equation. The summation of xi minus theta is equal to 0. Hence, the sample mean is the only 0 of the first derivative. So to verify that indeed this is a global maximum, then we're going to check, rather it's a local maximum, because we do not know yet if this sample mean x bar is a local maximum. It's just an extremum. So we're going to take the second derivative of our likelihood function and then evaluate it at the value of theta equal to the sample mean. If it is less than 0 or the value is negative, then we can be sure that our theta hat equal to the sample mean x bar is a local maximum. Okay? Kasi ito dito, sa first pa, is just a local extremum. Hindi natin alam, baka local minimum siya or local maximum. So if we're going to take the derivative of that, the second derivative of our likelihood function, ewan ko kung magkasya ito. Say the second derivative now of our likelihood function with respect to theta. Okay, so we're going to use this Itong part na to sa itaas. Ito. Say we consider this ito. Function f. Consider this as a function g. Constant lang naman yung sa itaas, no? So, yung other factor, so we can have 1 over 2 pi quantity n over 2. So the derivative of the product fg would be equal to f times the derivative of g plus g times the derivative of f. So copy natin yung f function. So they have the exponential. They have negative 1/2. The summation of x sub I minus theta quantity square. Okay, we copy f. And then we take the derivative of g. So yung derivative of g, ang g natin, we have the summation of xi minus theta. So in this case, we have now the summation of negative 1. I from 1 up to n. Plus, you copy g, no? The copy function g, the summation of xi minus theta. Then after that, you're going to take the derivative of f. So we have exponential of negative 1/2. We have the summation of x sub I minus theta quantity square. Yan. And then multiply by, dito na sa baba na lang, no? Kasi kulang siya. Negative 1/2. So we have here negative 1/2 times 2. We have here the summation of x sub I minus theta times negative 1. By the way, we're going to evaluate this. Theta is equal to the sample mean. Okay, so theta is equal to the sample mean. Okay. So if we're going to evaluate theta, no, if we're going to evaluate the theta is equal to the sample mean, so mangyayari dito sa part na to, itong theta equal to the sample mean. Obviously, the summation of the deviation of every observation from the sample mean, I from 1 up to n, that will be equal to 0. So the whole second term will be equal to 0. So yung maiiwan na lang dito, yung first term. So yung first term, evaluate na natin. Then you have 1 over 2 pi n over 2. We have here the exponential, negative 1/2, the summation of x sub I minus the sample mean square, I from 1 up to n. Okay. Yeah, wala na tong wala na pala to. Exponential. And then we have here the summation of negative 1. So we have here negative n. Obviously, this is less than 0. Kasi itong part na to, ito, positive ito. But the second one, ito, negative. So the product is negative. So the second derivative, by the second derivative test, so that would mean that our theta hat equal to the sample mean x bar is a local. So implies lang yan siya. Implies that theta here equal to x bar is a local. Local maximum lang siya. Yung kanina, extremum. Now, using the second derivative test, theta equal to x bar is a local maximum. So here it says the x bar is the only extreme point in the interior and it is a maximum. That's a local maximum. To finally verify that X bar is a global maximum, okay, we must check the boundaries, no? The boundaries from the positive infinity to and negative infinity. So by taking the limit, obviously, we establish that the likelihood is zero at positive and negative infinity. So kung i-check natin yan dito, that is the likelihood function of our parameter theta given x. Okay, it approaches to zero as our parameter theta approaches to positive infinity or negative infinity. Pwede naman yan. Pwede naman makita yan using our likelihood function. Diba? If this theta approaches to positive infinity, it approaches to positive infinity. So that would be e to the negative, no? E to the negative infinity. So ilagay mo yan siya sa denominator. That would be 1 over e to the positive infinity. And that would be equal to positive infinity yung denominator. So 1 over positive infinity, parang it approaches to positive infinity, that would be equal to 0. It approaches to 0. Totoo ito. It approaches to 0. Same thing if we're going to take theta here to be negative infinity. So the likelihood function of theta given x approaches to 0 as theta approaches to positive or negative infinity. Hence, we conclude that x, no, this x hat, rather the theta hat is equal to x bar. So this is now the estimate, no, the estimate of our unknown population parameter theta is a global maximum. Therefore, we conclude that our maximum likelihood estimator, which is actually a function of our sample, we have the big, no, big na siya, which is actually a random variable, the statistic x bar. Okay, so that's an illustration, simple illustration of our technique, no? Maximum likelihood estimator. So another way to find an MLE is to abandon differentiation and proceed with a direct maximization. So this method is usually simpler algebraically, especially if the derivatives tend to get messy. But sometimes harder to implement because there are no set rules to follow. So one general technique is to find a global upper bound on the likelihood function and then establish that there is a unique point for which the upper bound is attained. By the way, this given expression here, for example, if we're going to take it separately, no, the finite summation of the square deviation of x sub I, no, the deviation of x sub I from A is minimum. We know that if it's minimum if A is equal to the sample mean. So we need to say that this expression here on the left hand side is greater than or equal to the expression on the right hand side of our inequality. So with equality, if and only if A is equal to the sample mean. So this implies that for any theta, no, for any theta, alaman natin, no, from here, no, from here, okay, from here, say if we're going to multiply both sides by negative 1/2, then the sense of inequality is being reversed. So negative 1/2, summation. Yung summation, nakalimutan ko. So we have here negative 1/2, then we have here the summation, x sub I. Hindi ko nila ilagay yung index ng summation natin na. Okay. So it's being reversed. If we're going to take the exponential function both sides, then we have this. Then after that, pwede natin we multiply both sides by 1 over 2 pi raised to n over 2. So e to the negative 1/2 the summation of x sub I minus theta quantity square, okay? And then this is less than, since we multiply by a positive value, so uh, the sense of inequality is being preserved. So e to the negative 1/2, then we have mhm. Okay, so we have the summation of x sub I minus x bar quantity square. So this would mean that the likelihood function of theta given x is less than or equal to the likelihood function of okay, so that would imply, no, imply that the likelihood is maximized, no? The likelihood function is being maximized when the value of theta, when the value of theta or the estimate of theta is equal to our sample mean x bar. Okay, that's why the maximum likelihood estimator of our parameter theta, which is a function of our sample, we have now this big, no, x bar. Kasi yung pinakita ko ito, no, pinakita natin ito because hindi na natin hinanap yung derivative, no, the derivative of our likelihood function. Okay, so in most cases, especially when differentiation is to be used, it is easier to work with the natural logarithm of our likelihood function of theta given x. So we have log of the likelihood function. Then we're going to work on the log likelihood function directly. So this is possible because the log function is strictly increasing on the interval 0 to positive infinity, which implies that the extrema of the likelihood function and the log likelihood function coincide. Okay, so mathematical lang masyado yan, no? If we're going to look at the graph of the log function, it's actually, no, parang ganito yung graph niya. Oops. Ito yung graph niya. Say 1. Okay. This is 1. Yan yung graph niya ng ating uh, likelihood, log function. Okay, so let's have an example here in which we're going to apply the log likelihood function. So let x sub 1 up to x sub n be IID Bernoulli with parameter p, the probability of success. Then the likelihood function is, okay, we have here likelihood function of the parameter p given the sample, observed sample x. We have these, the product of the probability mass function p to the x sub I times 1 minus p to the 1 minus x sub I. Okay, so this is equal to p to the summation of x sub I. And then we have 1 minus p. We have here the summation of 1 minus x sub I. And furthermore, this will be equal to p to the summation of x sub I. And then 1 minus p. 1 minus p, the summation of 1, that is n, and the summation of x sub I. So if we're going to let y here be equal to the summation of x sub I, then we have p to the y, 1 minus p, n minus y. Okay, so say we're going to find the log likelihood function for this. Okay, so we have here the log likelihood function of p given x. Okay, we have the log of p to the y, 1 minus p to the n minus y. The log of the product is equal to the sum of the logs. So we have the log of p to the y plus the log of 1 minus p to the n minus y. Then using the property of the logarithm, then we have here. Okay, now you have that result now. So if we're going to determine the maximum likelihood estimator for our parameter p, we consider two cases here. First, consider that y is greater than 0 but less than n. Then if we're going to differentiate the log likelihood and setting this equal to 0, then it will give us the solution that our maximum likelihood estimator p hat is equal to y over n. It is also straightforward to verify that y over n is a global maximum in this case. So I'm going to show why that y over n is a global maximum for this case. So taking the derivative of the log likelihood, equating it to 0. So kunin mo natin yung derivative of the log likelihood with respect to p. Okay, so we have here y over 1 minus p, and then n minus y. So we have 1, and then times the derivative of 1 minus p, they have negative 1. Okay, so we have here y over p plus a minus na siya. Okay, so we have here n minus y, 1 minus p. So if you're going to equate this to 0, okay, equating that to 0, it implies we have here 0, we have y times 1 minus p. We multiply both sides by p and 1 minus p. Then n minus y, 1 minus p. So we have y, yp, and then in this case, oh, sorry, not 1 minus p here. We have only p. So we have np plus yp. The sum of these two terms is equal to 0. Okay, so implying now that our p or n minus np is equal to y, p is equal to y over n. So this is just a candidate, no? A candidate. It's a local extremum in this case. It could either be a local maximum or a local minimum. But if we're going to determine the second partial or the derivative, okay, say the second derivative of our likelihood function with respect to p, okay, dito tayo, no? I-simplify muna natin dito. So blue part, we have here y to the p to the negative 1, and then we have here minus, okay, n minus y, 1 minus p raised to the negative 1. So ito yung gagamitin natin na expression para sa second derivative. Okay, so for the second derivative, we have negative y over p square. Positive na siya, no? Sa denominator man natin inilagay. So we have plus, okay, plus, we have here n minus y, and then 1 minus p raised to square times negative, then negative 1. Evaluate this at p is equal to y over n. So evaluate natin yan sa p is equal to y over n. So sabihin natin negative y, p square minus n minus y over 1 minus p quantity square. Then we evaluate that to p y over n. So pag-evaluate natin yan, we have this result. We have negative n square over y minus n square over n minus y. And obviously, this is less than 0. So by the second derivative test, by second derivative test, this implies that p hat or p hat y over n is a local lang muna siya. It's a local maximum. So if we're going to verify it's a global maximum, kulang pa yan kasi kulang yung sa space natin. Verify it's a global. So to verify that y over n is a global maximum, so we're going to evaluate it on the endpoints of our parameter space. So in this case, 0 and 1. Okay? So check muna natin. As p approaches to 0, obviously, then the log likelihood function of our parameter p given our sample, it approaches to negative infinity. Okay? Ito naman yung ating log likelihood function. Ito na part. So, itong part na to. So, if p approaches to 0, the log of 0, itong part na to, the log of 0, p approaches to 0, no? So, the log of 0, negative infinity. And then log of 1, that is 0. So, in this case, this is 0. So, the log likelihood function approaches to infinity. Kasi log of p here, log of 0, infinity yan. Infinity yan. Kung p 0. Kung ito siya 0. Ito siya, log of 0, or rather, log of 1 is equal to 0. So, ang second term, 0. So, negative infinity. Pangalawa, if p approaches to 1 on the other side, then check. Then the log likelihood function again, here, of our parameter p, given our sample, also approaches to negative infinity. Pwede naman natin tingnan yan dito ulit. Okay, so kung ang p approaches to 1, so ano yung log of 1? So in this case, 0 ito. Log of 1, 0 yan siya. So log 1 minus 1, so log of 0, so log of negative infinity. So it approaches to negative infinity. Okay? So obviously, the log likelihood function attains its maximum when the value of p is equal to y over n. So this implies now that the p hat, which is equal to y over n, is a global maximum. Okay. And then second case, we have here a second case when we consider y is equal to 0 and then y is equal to n. So the log likelihood function, we have now n times log of 1 minus p if y is equal to 0. Okay? If y is equal to 0, makita naman natin yan dito, no, sa ating formula. If y is equal to 0, itong maiiwan, n times log 1 minus p. If y is equal to n, this would be 0. So n log of p. Okay, so from that, we are able to obtain this piecewise function. Okay, piecewise function. So in either case, the log likelihood function is a monotone function of p. Because we have here an expression of logs, logarithm lahat. So kung titingnan natin yung graph niya, no? Kung titingnan natin yung graph ito, parang ganun. Say this is 1. Okay, yan yung graph natin. It's either of the two, huh? It's either of the two. So when y is equal to 0, then we have n log of 1 minus p. So from this interval, kasi yung p, nandito mo lang sa interval natin dyan. Yan lang. 0 to 1 naman siya. No? So it's a monotone function. Okay? So the log likelihood function, ito yung log likelihood function. In either case, ito yung graph ng ating log likelihood function. So the log likelihood function attains its maximum, no? Or attains the maximum when the value of p will be equal to y over n. That is why, in either case, no, the maximum likelihood estimator, whether in case 1 or case 2, the maximum likelihood estimator for our parameter p is equal to the sample mean. Ito yung y over n. Y over n, we know that y is equal to the summation of x sub I. So the summation of x sub I over n, or we could be also equal to the sample mean. Pwede yung ganun. So another illustration, no, another illustration of the maximum likelihood estimation procedure in which we use the log likelihood instead of applying directly our differentiation to the likelihood function. Okay, another example, no. Uh, one other point to be aware of when finding a maximum likelihood estimator is that the maximization takes place only over the range of parameter values. So in some cases, this point plays an important part. So consider the example below. We have the restricted range maximum likelihood estimator. So let x sub 1 up to x sub n be IID, coming from a normal distribution with mean theta and variance is equal to 1, where it is known that theta must be non-negative. Usually, no, dapat yung theta natin, we'll say mean, it ranges from negative infinity to positive infinity. But in our problem here, we assume that our theta be a non-negative value. So theta is greater than or equal to 0. So with no restriction on theta, we saw that the maximum likelihood estimator of theta is the sample mean. We have that in our previous example. However, if we consider the sample mean to be negative, so it will be outside the range of the parameter because we restrict the value of our unknown parameter theta to be non-negative. So if the sample mean is negative, it is easy to check that the likelihood function is decreasing on the parameter theta for theta to be greater than or equal to 0. And it is maximized at theta hat is equal to 0. So hence, in this case, the maximum likelihood estimator of our parameter theta is theta hat is equal to the sample mean x bar if the sample mean is non-negative. But theta hat is equal to 0 if the sample mean is negative. Pwede natin ito ma-check, no? By looking at the graph of our likelihood function. Say, itong okay. So this is the graph of our likelihood function. This is our sample mean, x bar. Okay. So if x bar is negative, if it is negative, so nandito yung 0. Nandito yung 0 na point. So ang x bar negative siya. So in this case, x bar here is less than 0. Okay, it's less than 0. We see that the likelihood function of theta is decreasing on theta. Makita naman natin dito sa graph natin, di ba? It is decreasing on theta. For theta, no, for theta to be greater than or equal to 0. So decreasing siya dito nga part, dito na part, decreasing. Ito, na decreasing. Okay? So the likelihood function attains its maximum, when the likelihood function attains its maximum if theta hat is equal to 0. Yan itong maximum niya dito. It attains its maximum when theta hat is equal to 0. Ayan, case yan na when the sample mean is negative. Yung pangalawa naman, alam naman natin yun, sa graph. Na-solve natin ito in our previous example, pero kung tingnan natin yung sa graph, okay, so ito yung sample mean natin, x bar. So in this case, nandito yung 0 natin. Nandito yung 0 na value. So in this case, our sample mean is greater than or equal to 0. Makita naman sa graph, the sample mean. So the likelihood function attains its maximum. Nandito, dito sa maximum niya, it attains its maximum. Okay, so let me proceed. A useful property of maximum likelihood estimators is what has come to be known as the invariance property of maximum likelihood estimators. So not to be confused with the type of invariance discussed in chapter 6. Okay, suppose that a distribution is indexed by a parameter theta, but the interest is in finding an estimator for some function of theta. So we have now tau of theta. Okay, finding an estimator for some function of theta, say tau of theta. So informally speaking, the invariance property of the maximum likelihood estimators says that if theta hat is the maximum likelihood estimator of the parameter theta, then tau of theta hat is the maximum likelihood function of the function of the parameter tau theta. Say for example, if theta is the mean of the normal distribution, okay, mean of the normal distribution, so this would imply, okay, this would imply that the maximum likelihood estimator of our parameter theta, we have the sample mean, x bar. We have solved that before in our example. If theta is the mean of the normal distribution, then the maximum likelihood estimator of theta, we have theta hat is equal to the sample mean, x bar. So using the invariance property, so the maximum likelihood estimator of sine of theta. So in this case, this is a function of our parameter theta equal to sine of theta. So the maximum likelihood estimator of the function of theta, which is tau of theta, is this tau of theta hat. Okay, tau of theta hat. So that means we have tau of x bar, and that is equal to sine of x bar. Okay. So there are, of course, some technical problems to overcome before we can formalize this notion of invariance of maximum likelihood estimators, and they mostly focus on the function of our parameter theta that we are trying to estimate. So if the mapping tau to tau of theta is 1 to 1, when you say 1 to 1, that is for each value of theta, there's a unique value of tau of theta, and vice versa. By the way, do you have class after this?
Wala
Wala.
po.
Sige. Tapusin natin hanggang 3:30 na lang ha. Nagsimula kasi tayo ng 2 o'clock. Okay, so if we have a mapping on the parameter space, sabihin natin parameter space. So we have here, that's the parameter space to another parameter space. Say this is our parameter theta. Ito yung mapping niya, no? That's we have tau. Okay, so this theta has an image under tau. We have here tau of theta. Ayan, tau of theta on the parameter space. If it is 1 to 1, 1 to 1, ang implication nga ng 1 to 1, kung ang images ng dalawang elements sa ating domain, say tau of theta sub 1 equal. That's we assume, no? Equal yan sila. So this would imply that theta sub 1 will just be equal to theta sub 2. That means for a one-to-one function. So then there's no problem if we have the function tau is a one-to-one function. So in this case, it is easy to see that it makes no difference whether we maximize the likelihood as a function of theta or as a function of tau of theta. In each case, we get the same answer, whether we manipulate it using a function of theta, using theta or the function of theta. So if we let eta to be equal to tau of theta, ito ngayon, equal siya sa eta. Okay? Ang tau of theta. Then the inverse. Obviously, we know that if we have a function that is 1 to 1, then we could find the inverse. So the inverse of tau, that is tau inverse, tau to the negative 1. So we apply lang tayo dito in this case, no? Mag-apply tayo tau inverse of eta equal to tau inverse of tau of theta, and that would be equal to theta. So we have here. So tau inverse of eta is equal to theta is well defined. And if we're going to determine the likelihood function of the function of our parameter tau of theta, written as a function, take note, written as a function of eta because we equate eta to be equal to tau of theta. So as a function of eta, it's given by this. So gagamitin lang natin itong L star. It's a function of eta, so we have L star of eta given our sample. And then by definition, we have here the product of the, or the joint density. So we have f of x sub I given tau inverse of eta. Okay, so we have that. Since we know that this is equal to eta. Itong part na to is equal to eta. So, and then using our likelihood function now, which is a function of theta. Kasi theta ito is a function of theta, so L of tau inverse of eta given our sample x. So if we're going to take the supremum, if we're going to take the supremum of all likelihood functions of eta given x over all eta, so that would be equal to the supremum of L of tau inverse of eta given x. That's for all eta again. Using this fact above, and then since tau inverse of eta is equal to theta, then that would be equal to the supremum of all the likelihood functions of theta given x over all theta. By the way, no, this is for the case when tau here is 1 to 1. Thus, the maximum of this likelihood function of eta, it is attained at eta is equal to tau of theta, okay? And the tau of theta is actually, since tau is 1 to 1, that's why we have here equal to tau of theta, showing that the maximum likelihood estimator of our tau of theta to be equal to tau of theta hat. That's for the case when tau is 1 to 1. But if tau is not 1 to 1, then for a given value eta, there may be more than one value of theta that satisfies tau of theta equal to eta. Mean to say many to 1 siya. So kung ito yung ating parameter space, yan, parameter space, meron tayong theta 1 dyan, theta 2, in which yung image nila isa lang. In this case, then tau of theta 1 is equal to tau of theta 2, the image no, of theta 1 and theta 2 under theta are equal in this case. So there are two. We can equate this equal to the specific value, which is eta. So there may be more than one value of eta, or theta rather, that satisfies tau of theta is equal to eta. Sa example ko, dalawa yung kinonsider ko. We have this theta sub 1 and then theta sub 2. So in such cases, the corresponding between the maximization over eta and that over theta can break down. For example, if theta hat is the maximum likelihood estimator of theta, there may be another value of theta, say theta sub 0, for which the maximum likelihood, no? Itong theta hat, tau of theta hat will be equal to tau of theta sub 0. Because we know that our tau is not 1 to 1. So tau is not 1 to 1, we proceed by defining for a function of our parameter theta an induced. So we have here an induced likelihood function. Still we use this likelihood function L asterisk or L star given by. So in this case, the likelihood function of eta given our sample, we're going to consider now that the supremum when we attain or the value, this likelihood function attains the maximum. Take the supremum of all the likelihood function of theta given x on this given set. For this set, no, the set of all theta such that the image of theta under tau is equal to eta. The supremum of that likelihood function. So the value eta hat that maximizes the log likelihood function, rather the likelihood function of eta given x, will be called the maximum likelihood estimator of theta, which is actually equal to tau of theta. So it can be seen from 7.2.5 that the maxima of L star, okay, the maximum of L star, and then L will coincide for that. Okay, so we have here theorem 7.2.10. We have the invariance property of the maximum likelihood estimators. If theta hat is the maximum likelihood estimator of theta, then for any function of tau of theta, then the maximum likelihood estimator of tau of theta is tau of theta hat. So using this theorem, we see that the maximum likelihood estimator of theta square, so the square of the normal mean, take note, is a normal mean, normal siya. Okay, so the maximum likelihood estimator of theta is the sample mean x bar. So the maximum likelihood estimator of the square of theta will be the x bar square using theorem 7.2.10. Uh, for a more complicated function, say the maximum likelihood estimator of the square root of p1 minus p, where p is a binomial probability, it is given by the p hat here. Actually, the p hat here is the maximum, no? P hat the maximum lang p hat here. So, uh, sorry, is the MLE, maximum likelihood estimator of our parameter. So, kung ito yung ating function of p, then the estimator would be a function of our maximum likelihood estimator of p. That's according to theorem 7.2.10. Okay, so let me proceed. The invariance property of the maximum likelihood estimators also hold for a multivariate case. There's nothing in the proof in theorem 7.2.10 that precludes the theta from being a vector. So if the maximum likelihood estimator of the vector of parameters theta sub 1 up to theta sub k, so we have here a vector of estimators, theta sub 1 hat up to theta sub k hat. So if we're going to consider a function of the parameters, which is tau of theta sub 1 up to theta sub k, then the maximum likelihood estimator of the function of our parameters, tau of theta sub 1 up to theta sub k, is the function. No? It's a function of the maximum likelihood estimators, tau of theta sub 1 hat up to tau of uh, rather tau of theta sub 1 hat up to theta sub k hat. So in this case, no, yung ating parameter is actually a vector. Parameter theta is a vector of parameters theta sub 1 up to theta sub k. So it's multidimensional. It's multidimensional. We can still apply, the procedure that we have in the maximum likelihood estimation procedure. Say, for this problem, let x sub 1 up to x sub n be IID normally distributed with mean theta, and then variance sigma square where both theta and sigma square unknown. So, ibig sabihin yung mean niya is theta, ang variance niya is sigma square. So, ito pala, hindi yan mu, kundi theta ito, no? Theta yun siya. Then, the likelihood function of our parameter, pwede ganun, no? Both na siya na vector. Vector yung sample natin, vector din natin yung ating parameter. Equal. Or pwede mo i-specify yung theta, vector of theta, we have these parameters, theta and sigma square. Parang ganito ha. Ito, vector. Yung mga components niya, ito, theta isa, tsaka sigma square. Okay, so this is our likelihood function. Since it's easier to manipulate if we're going to take the log likelihood function. So ito yung log likelihood function. We have now, ito no, 3 terms. Meron tayong 3 terms. Pwede naman ma-apply yan no, sa log likelihood. Dito, the log of E, ito yung may iwan na lang sa the log of E. The log of the product will be equal to the sum of the logs And then applying that property of logarithm, we arrive at this log likelihood function. Taking the partial derivative, no? Partial derivative of this log likelihood function with respect to theta and sigma square. Okay, so we have this. And then after that, we're going to equate this to 0. Say for example, no? Take the, lang ha? Itong first term natin dito. Take the partial derivative with respect to theta. So that will be 0. Yung sa first term. So 0 ito. Ito sa first term. 0. Ito din. 0. Kasi constant lang naman yan. Okay? So dito tayo sa third term. With respect to theta. Okay, so the derivative of the sum will be equal to the sum of the derivatives. So, meron tayo dito. So, take natin yung derivative niya. So, yung derivative niya dito, so, meron tayong negative 1 half. So, negative 1 half. Kuhan ko na lang, no? Yung summation. So, we have here 2 times x sub I minus theta. And then, over sigma square. And then, times negative 1. Cancel yan, cancel yan. So, positive. Kaya ito, kuha natin yan. Dali lang naman. Sa second naman, erase ko lang. Sa second, take the partial derivative of the log likelihood with respect to sigma square. So sa sigma square, ito wala itong sigma square, so this is 0. Yung pangalawa, merong sigma square, so 1 over sigma square times 1. So negative n over 2 times sigma square. Okay, tama yung first, yung itong term na to. Ito din dito sa third term. Okay? So, pwede niyan siya, no? Pwede may express nito. Ito. Pwede may express as sigma squared to the negative 1. Then meron tayong 1 half. Then we have the summation of x sub I minus theta square. To take the derivative of that with respect to sigma square. So negative 1. Ito negative 1. Then sigma squared to the negative 2. Then 1 half. Summation of xi minus theta quantity square. Kaya yung hindi yan equal ha. The derivative implies para sure tayo na baka sir, ba't in-equal mo? You take the partial derivative with respect to sigma square. Okay, yan. Ganun. So, yan yung result. That will be equal to negative may negative pa man siya sa istaas pala. May negative 1 half. So, negative 1 half. May negative 1 half pa yan dyan. Negative 1 half. So, naging positive siya. So, 1 over sigma square square. Sigma square square. And then, positive na siya, no? Summation of xi minus theta square. Okay, ito yung result. Mayroon pa siyang 2. So, sigma square square, that is sigma 4. 2. Nakuha na natin yung second, no? Then you equate this to 0. Setting these partial derivatives equal to 0. So, for the first, ito yung system natin. So, we have now 1 over sigma square, the summation of xi minus theta. Hindi ko nalalagay yung index of the summation na equal to 0. So, summation of xi minus theta equal to 0. Okay, so we have here, dito na lang, we have here the summation of x sub I minus n theta equal to 0. So theta would be equal to 1 over n summation of x sub I. Again, this x bar here is still a candidate. No? Candidates. It's a local extreme. We're going to verify it's a local maximum, and at the same time, it's a global maximum. Okay, and then for the second one, meron tayong negative n over 2 sigma square, and then plus 1 over 2 sigma to the 4. So we have here the summation of xi minus theta quantity square equal to 0. So multiply both sides by uh, run muna natin. Pwede natin i-transpose on the other side. N over 2 sigma square. Okay, multiply both sides by sigma to the 4. No? Or multiply both sides by no, sigma to the 4. Merong cancel itong 2. Sigma to the 4. So, ay may iwan dito. 1 over n is summation of xi minus theta square. Then we have here sigma square. Or you say sigma square is equal to 1 over n 1 over n, the summation of xi minus, we know already what is theta. So theta here is x bar, quantity square. But still again, this is a candidate of a local extreme. Okay, setting the partial derivatives equal to 0, solving it yields the solution. The theta hat is equal to the sample mean, theta bar, that sigma square hat is equal to this expression. So to verify that this solution is in fact, yun, importante kasi it's a global maximum. Recall that if theta is equal to if theta is equal to the sample mean, we know this already, no? Because itong part na to, ito, this finite summation of the squared deviation of every observation minus theta, this would be minimized. It's minimum when theta is equal to the sample mean x bar. So if theta is not equal to the sample mean, then this expression, this summation na green would be greater than the summation, finite summation of the squared deviation of x sub I minus x bar. Okay, so global, no? Maximum na yung sample mean. Hence, for any value of theta, we have here, ang implication yan, no? Parang yung kanina, say, nag-multiply ka both sides by negative 1/2, then the sense of inequality is being reversed. Malalaman mo dito, kung titingnan mo yan dyan, no? Reverse, dito theta, dito x bar, pero palit na sa kabila, nandito na sa left-hand side yung x bar, nandito yung theta sa right-hand side. So it's being reversed, raise that to e, multiply, you apply exponential to those expression, and then you multiply both sides by 1 over 2 pi sigma square raised to n minus 1, and we're able to get the likelihood function. So yung implication nito, no, the implication for this, that the likelihood function given our sample is being maximized, at the sample mean x bar. What about, no, what about yung ating sigma square? Paano natin malaman, makukuha yung na global maximum yung value ng sigma hat square, which is equal to 1 over n, the summation of the square deviation of x sub I minus the sample mean. So it says here, therefore verifying we have found the maximum likelihood estimators is being reduced to a one-dimensional problem. Okay? One-dimensional problem na lang. So that means that we have, alam naman natin yung theta. So one-dimensional problem na lang, ganito. Kasi yung theta is equal to the sample mean. Okay? So, okay, so parang ganito yon. I have 2 pi sigma square raised to the negative n over 2. And then here we have the exponential function. We have negative 1/2 the summation of x sub I minus x bar. It's being maximized, no? Quantity square over sigma square. Okay, so yan yung ating likelihood function in no, parang one-dimensional na siya. We have only one parameter, which is sigma square. And after that, we're going to apply the log. So we have the log likelihood function. Okay. So dot yan siya. Hanggang makuha natin to, log of the product will be equal to the sum of the logs. And then also apply the property of the logarithm. Then we're able to have this negative n over 2. Then we have a log of 2 pi. Then we have also negative n over 2. Then we have here the log of sigma square. The log of the exponential. Lang. We have ang kanyang power na lang pala. So we have here negative 1/2, the summation of x sub I minus x bar, quantity square, we have sigma square. Ayan. And then if we're going to get the partial derivative of this, no? Hanapin yung derivative. See the derivative of this log likelihood function with respect to sigma square. With respect to sigma square, so yung first term natin will be 0. Second term, you have negative of n over 2. And then we have here 1 of. And then this one, we have a raised to the negative 2, negative 1. So we have here positive. Okay, we have positive 1/2. We have here sigma to the 4. And then we have summation of x sub I minus x bar, quantity square. We equate this to 0. Okay. So we have negative n over 2 sigma square. Diretso na lang tayo. Implies, no? So this is equal to ayan, nagkuha naman natin kanina. We have solved this already a while ago. Okay, so we have here sigma square is equal to 1 over n summation of x sub I minus x bar quantity square. And then take the second derivative. Take the second derivative. D sigma square, okay, second derivative of that, square, and then yan, square of the log likelihood function given x. So dito tayo. Dito na part, pwede natin ma-simplify ito. Okay, so this is negative n sigma square to the negative 1 over 2, then plus 1 half sigma square to the negative 2. Then we have the summation of x sub I minus x bar. By the way, we want to check or want to determine if indeed sigma hat or sigma square hat equal to this is a global maximum. So we're going to apply the second derivative test. That's why we need to determine the second derivative of the log likelihood function. Okay. So in this case, in the first term, negative of negative 1 times negative n. So we have positive. So we have here n over 2, then sigma to the 4. Okay, sigma to the 4. Then ang sa kabila naman, magiging siyang negative 2. Negative 2, so cancel siya sa 2. Itong part na to, no? Cancel siya sa 2. So, yung maiwan niya, negative siya. Negative 1, minus 1, minus 3. So, sigma to the 6. Then, maiwan pa rin ito. X sub I minus x bar quantity square. We ever take this, no? And then evaluate it at sigma square. Dito ko na sulat na sigma square is equal to 1 over n summation of x sub I minus x bar quantity square. So evaluate sigma square is equal to 1 over n summation of xi minus quantity square. Obviously, if you're going to evaluate that, no, pag-evaluate mo, dot, diretso na lang yan, hindi ko na ipakita. We have negative n square, simplify. Then we have here 2 times, we have here the summation of x sub I minus x bar, quantity square, square. And obviously, you can see that it's indeed less than 0. So by the second derivative test, sabi naman kasi dito, it is straightforward, no? This is straightforward to do using univariate calculus. And in fact, the estimators x bar are the MLEs. So kaya dito ngayon, so by second derivative test, yung sigma square, which is equal to 1 over n, the summation of xi minus x bar quantity square, is a maximum. Therefore, the x bar, and then here 1 over n, the summation of xi minus x bar quantity square. Okay, ano sabi doon? Are the MLEs. Are the maximum likelihood estimators of theta and sigma square. Okay, so 3:33 na. Meron pa tayong isang example dito, pero next meeting na lang ito. Okay, so any questions or clarifications regarding the maximum likelihood estimator or the maximum likelihood procedure in determining the estimate as well as determining the maximum likelihood estimators? Etong dito na part, no? Kasi dito sa last example natin, apply natin yung sa calculus na part. Ito dito, nalaman natin na yung likelihood function is being maximized at this sample mean x bar using this fact, no? Ito. hindi tayo nag-apply, no? Hindi tayo nag-apply ng derivative, no? The derivative of the log likelihood function with respect to theta, and then we do not apply also the second derivative of the likelihood function with respect to theta. Dito, sa pangalawa lang tayo nag-apply ng derivative, no? The derivative of the likelihood function with respect to sigma square, and then the second derivative of the log likelihood with respect to sigma square, and then we apply the second derivative test to determine that our value, or the value of our parameter sigma square would maximize our log likelihood function. Kasi dito sa last na example, no, sa example 7.2.12, before we proceed to the next method, yun, dalawa talaga. You take the partial derivative of theta sub 1 with respect to theta sub 1, the second partial derivative of theta sub 2 with respect to theta sub 1, and the partial derivative of theta sub 2 with respect the partial derivative of the likelihood function with respect to theta sub 2, and then the second partial derivative of the likelihood function with respect to theta sub 2. Ito yung usual, no? Then we're going to construct the Jacobian of the second order partial derivatives, and then evaluate this, no? Determinant, no? The determinant of this the determinant of this matrix, 2 by 2 matrix, evaluating at the value of theta sub 1 is equal to theta sub 1 hot, and then theta sub 2 is equal to theta sub 2 hot. Okay, no. So for normal log likelihood, these are the second order partial derivatives. Second order partial derivatives. The Jacobian of the second order partial derivatives. Kasi, itong part na to, dito, itong part na to, meaning to say, dito na example na to, yung theta natin, which is equal to the vector of theta and then sigma square. So, i-replace natin ito na ito yung theta sub 1 and then ito yung theta sub 2 based on our example. So, we're going to take the derivative, partial derivative, and then the second partial derivative with respect to these parameters, theta sub 1 and theta sub 2. I-explain ko na lang ito, kayo na lang mag-verify para next meeting, I'm going to proceed to the next method. Ito yon. Ang sinabi lang dito sa example na to use two-variate calculus to verify the function. So we have here a function. This actually refers to our likelihood function, or the log likelihood function has a local, take note, it's just a local maximum at theta 1 hot and theta sub 2 hot. It must be shown that the following three conditions hold. Okay, so the first order partial derivatives are equal to 0 or 0. Evaluating on this value, theta sub 1 is equal to theta sub 1 half, theta sub 2 is equal to theta sub 2 half. And then at least one of the second order partial derivative is negative. At least. So, or, kaya or siya, or. And then the Jacobian of the second order partial derivatives is positive. So, positive. Okay, assume na nakuha na natin to. Ang second order partial derivative. Yan. And then, if we're going to determine the Jacobian, which is actually the determinant of this 2 by 2 matrix. And then we're going to evaluate that theta is equal to this, no? Kasi theta is equal to x bar, sigma square is equal to sigma square hot. I-evaluate natin yan, substitute it to our determinant of this 2 by 2 matrix. And we have seen that it is indeed positive. Okay, so according to our example, then theta equal to the sample mean x bar, and then sigma square equal to sigma square hat uh, is a local, no, it's a local maximum. Okay, so I think that's all for this afternoon. Lumampas tayo ng 10 minutes. Pero okay, I think sana okay lang sa inyo. Okay lang ba?
Okay lang, sir.
Okay, so to wrap it up, no? I discuss one example for the method of moments, and then the second method, we have the maximum likelihood estimation procedure, in which we're going to determine the maximum likelihood estimator. Okay, so we can apply, say if we have only one parameter, then univariate the case in likelihood function. We take the first derivative of the likelihood function or the log likelihood function, setting that to 0, and then we obtain the critical value. It's just a what we call a candidate of our local extremum. And then applying the second derivative test on the second derivative of our likelihood function evaluated at the critical value of our likelihood function or log likelihood function. If it's negative, then that would imply that we attain or did we obtain the local maximum. So kung meron tayong mga endpoints sa ating parameter values, so evaluate it on the boundary points. If those boundary points, the value is lesser compared to the value of the critical or the estimate of our parameter, then conclude that we conclude that the maximum we obtain the global maximum. Pwede din natin i-apply sa no, if we have two multidimensional parameters. So, itong last na part. And then we can also apply yung invariance property. If we want to determine the maximum likelihood estimator of the function of our parameter. Okay, so that's all for this afternoon. Reserve your question next meeting na lang kasi lumampas na tayo. So I'm going to stop now the recording.